Okay, so maybe let's get started with the talk. Today we
Okay.
have with us Depen Morwani, who's a PhD student at Harvard. He's advised by Boz Barak and Sham Kakade, and he's interested in understanding mechanisms in deep learning. So with that, I think Depen, the stage is yours.
Yeah. Thanks for inviting me for the talk. I guess so. I'll basically start with the talk. So the main point of this talk will be to try to explain like why neural networks sort of choose to implement a given task in specific ways. So we have called this like feature emergence in neural nets, and we basically want to learn the origins behind why neural networks use like particular computational strategies for a task. So first of all, I'll go into some motivation for this question. So recently, we have seen like various works which have tried to sort of find like some specific structure within neural nets. So this nice work by in 2022 by Olson et al. Discovered induction heads within neural nets, which basically are some kind of circuits which can do context-based copying within transformers. So this was a very this basically is one of the structures which neural nets have. Okay, before going forward, I'll say like please feel free to stop me at any point if you have questions. I'm also planning to stop, but please feel free to ask questions during the talk. Um, Okay. So apart from this, there have been other works as well, which have identified like circuits which GPT-2 uses for for implementing a task called indirect object identification. So recently we have seen a lot of these works, which can sort of try to see like how neural networks implement a given task. So I'll try to say that this is not new. Like we have known it from quite some time. There is a lot of structure in trained nets. So there is a paper from 2013, like basically the word to vec paper, which basically shows that word embeddings trained using these generally tend to have linear structure, which basically means if we have embedding for king, man, and woman, it's likely that the embedding for queen is king plus woman minus man. So word embeddings trained using word to vec tend to have this linear structure. Apart from this, there have been works which have tried to which have shown that even the attention heads trained in neural nets discover some of this syntactic structure present in the language. Apart from this, we all already discussed what induction heads are. And then even in CNNs, we have seen like various feature detectors such as edge detector, shape detectors, etc. So we do know like there is a lot of structure which emerges in train nets. Um, so please let me know if there is any question. Sorry, yeah. Okay, so we do know that there is a lot of structure in train net. So now the main thing we will say that this is something like morphology and physiology of deep learning. So we have tried to sort of study till now like what are the structures inside the net. We have also kind of tried to study that what are the functions of these uh, structures, but I think that we have not really looked at an evolutionary perspective for these. Like we have not really tried to answer like why do these particular structures come up. Also, we don't know how do these particular structures evolve during training. Like most of these works are missing the evolutionary perspective for these particular structures which come up in a trained net. So this is going to be the main focus of this work. So we are going to try to answer like why these particular structure mechanisms come up. Even for the toy tasks, which I am going to cover in this work, it is surprising that we still don't know the exact trajectory about like how do these structures evolve during training. So although we can, there is like some fundamental way using which we can say why these particular structures or mechanisms are referred. Now we can still ask, like, do we really care about this why question or not? Like, why is this why question still relevant? I think we should care about it because of a few reasons. So one is it is really going to help us judge the behavior of the neural network under distribution shifts. So if we know exactly like what is the reason behind why these particular mechanisms come up, then we can really judge as to if the data set shifts in some way, or if the inputs to the neural net shift in some way, then how will the train network look like? Like we don't need to each time for each new data set really know like exactly how, like train a new net for every data set. We can also use this for explaining some of the failures of learning. Like if we know that transformers are not generalizing on a specific task, we can try to really see like what happened during the training, like why did the intended structures not come up. I believe this can also be used to modify the learning process to make the overall final mechanism more robust, fair, or whatever like nice properties we want in like the final uh, mechanism. So I think due to these reasons, like understanding why seems like an important question. Uh, okay, so I'll take a pause at this point and ask if people have any questions about the motivation for the work. Feel free to ask. Um, okay. Okay. So in that case, I'll go over the basic outline of the talk. So first, we'll cover some background necessary for the talk. Then we'll go over a particular case study of the task of modular addition, where we'll try to see all the technical tools as well as what particular mechanisms do neural network use, and why do they use that particular mechanism for implementing the modular addition task. Then we'll provide the final results using the same. Will not go into like the technical depth of group composition task, but will basically provide what using these tools what we can prove for general group composition task as well, and then we'll conclude with some future work. So before going into the talk, I'll first like to thank my wonderful collaborators from Harvard. Like without Ben, Costin, Rosie, and Sham, this work would not have been possible. So yeah. Okay, so let's start with the background for the talk. So this term will hear a lot of time in the talk. So let's first try to see what does the term inductive bias mean. So according to me, this means like any choice which we make during a training process, which affects the way neural networks chooses to implement a particular task. That could be called as the inductive bias of that choice. So this could be like the optimizer choice, or the regularizer choice, or basically the architecture which we use. All of these things have some effect on the final features learned, and all. So this is basically called like an uh, inductive bias. So now to give some examples of this. So for optimizer in a very simple task of over-parameterized linear regression, gradient descent is known to exhibit minimum L2 norm bias. This basically means that if there were many parameters possible for implementing a given linear map, gradient descent will implicitly choose the map which has the minimum L2 norm. Um, Similarly, an explicit L1 regularization is known to produce sparse parameters, generally in case of linear regression. So this is like like the bias of an explicit regularization. Apart from this, we also there have been recent works which are also trying to study the bias of various architectures, such as LSTMs versus transformers. So these are basically some different biases which have been sort of studied in the past. So the main inductive bias which we are going to focus on in the talk is the maximum margin bias. So let's define what that means in a simple setting of logistic regression. So let's consider a binary classification task where we consider the data set to be linearly separable. And in this case, the maximum margin solution is given by we want to find the minimum norm of the weights, and we'll consider the L2 norm of the weights. So minimum L2 norm of the weights such that we can classify this data set well. So what was shown in a seminal paper in 2017 was that when logistic regression is used, and we use gradient descent to train, the direction of the iterates implicitly converges to the maximum margin direction. So this is the maximum margin bias known for gradient descent for a simple linear classification setting. Let's see it. So this is basically a very toy data set, a 2D data set, where we basically ran gradient descent, and we see like if we start from the blue line and we keep on training gradient descent for quite some time, we basically see that the iterates, like the direction of the classifier, slowly converges towards the max margin direction. I guess so. The main point is that if we look at this red line, this red line was also a line which classifies this data set per perfectly. So there is no explicit reason for cross and entropy to prefer like the green line over this red line, but because of the trajectory that gradient descent takes, it converges to the max margin classifier. Are there any questions till now?
So one quick clarification. So this thing, does it assume that the initialization, does it assume anything about the initialization? That is, do
No,
we
it
have to
doesn't.
start at zero or something?
So not for cross and entropy loss. That's not true. Like
Okay.
you can basically start from any point as long as we get the loss down to zero. Like we can't use like very high uh, step sizes on gradient descent. Like we need to use a small enough step size so that the loss goes down to zero. We'll get to the max margin classifier.
I see. Okay.
Yeah.
Sorry, could you explain here why? So if you reach a point where the loss is zero and therefore the gradient of the loss is zero,
Uh,
like somehow, yeah.
Yeah, so the loss is not zero. So basically, when the weights are on the red line, it is perfectly classifying the thing. But if for logistic regression, we have exponential tails. So till the weight norm does not really go to infinity, the loss is not going to go to zero. So that's why like the loss
Yeah,
loss
yeah,
still
yeah.
has some gradient. Yeah. Any other questions? Okay, so I'll move forward. So this is basically the max margin bias, which is known by the 2017 work for gradient descent on cross entropy loss in case of linear classification. So now let's dive into our work. So we'll have the case study of modular addition, and we'll basically try to see like some simple neural networks trained on modular addition. How do they implement this particular task? So this is basically going to be the setup. So we basically want to learn something like we basically want the neural network to learn A plus B mod P, where A and B are two integers less than P, and we basically just want to ask the new neural network to learn this task. The way we are going to structure the net, it's going to be a one layer neural net with some activation function sigma. And to note that A and B are going to be provided as one hot input vector. So we are going to basically these are of dimension P. And then then we are basically going a single neuron within the neural net is going to produce a p-dimensional output, which basically represents the p possible classes of the output. And the entire neural net is basically going to be simply a sum of these many of these single neurons. So this is a specific structure which is true only for single hidden layer net, and we are going to use this structure in the proofs a lot. So basically, the main thing we want to get out of this slide is that a single hidden layer neural net, the output can be expressed as the sum of the outputs of a single neuron. Um, Okay, so we are going to use this fact in sometime. Okay, so now why is this particular task good to study? So there have been various recent works which have sort of shown like intriguing phenomenon on this task. So I guess the work by 2022 in by Power et al. Basically showed that when we train neural nets for learning the task of modular addition, they tend to exhibit something like grokking, which is basically that the validation accuracy goes up a lot of time after the train accuracy has gone up. So there are like various questions which we can ask like within this task. Like we can really ask like why is there a phase transition? Like why does the train accuracy go up in one shot? Why does the validation accuracy go up in one shot? And is there really no progress before this point? Like the neural network, does it suddenly learn all the things it needs to learn during this small phase? And we can definitely ask like, why is there such a gap between val and train? We can also ask like, what mechanism does the train net use, and why does it use that particular mechanism? So all these kind of questions can be asked on this task of modular addition. And this talk is going to focus particularly on the last question. There have been previous works which have explored the other two questions. So let's go into this thing. So now let's think about what are the various ways we can actually try to solve this modular ed addition task. And let's take like simple example of a clock. So let's take if the current time is 9 and we really want to know what will be the time 5 hours from now, there are various computational strategies possible. We can literally count up one by one, and we can memorize the fact that after 12 we need to switch to 1, or we can simply do an addition followed by a subtraction where we somehow know if the number is greater than 12, then we need to subtract 12. We can memorize the whole thing. We can just know like if I'm provided two things, I can just have like a memory table and I can provide the answers to. Or there could be something like really like what the clock does. Like we can really imagine a clock and move the R end by a specific angle, and then we can see, okay, now it points at 2, and that's why the time is 2. So like this might seem like a very silly thing, like all these things, but the main point is like the neural networks can do this. Like neural networks can, given a sufficiently wide neural net, it can literally just memorize the entire training set. It is possible, but what we are going to show, what a previous work showed is that no, neural networks tend to use this clock visualization algorithm for implementing the modular addition task. So what is this algorithm in terms of what like a neural net does? So first, it maps the given inputs a comma b to exponential space or to cosine and sine space. This is done in the embedding weights. Then it somehow uses the activation and all these things to implement the product of these two things, so that we get something like a plus b mod p. So now we can think of this as like we have like cosine of a plus b mod p and sine of a plus b mod p. Now finally at the output, what it does is that it rotates it back by minus c. So for a given logit c, we rotate it back by minus c, so that now the output which we have, it is specifically maximized at the point when c is a plus b mod p. So this is how a classifier works. So we really want the final output, which has which is a p-dimensional output, to be maximized at the point where C is A plus B mod P, and this thing is maximized at C equal to A plus B mod P. So this is the algorithm which Nanda et al. Discovered on some one-layer neural nets behind how they tend to implement this particular task. Is there any question? Okay, so I'll move forward. So the goal of this work was basically try to explain like why do networks learn these particular Fourier features for the given task. And our main approach is going to be that we are going to show that every max margin solution need to have these uh, features. Like basically, we are going to show the only way the neural net can minimize the norm of its weights is by using these features. And the way this connects to gradient descent and all these things is that we can theoretically show that for the network which we have, if we use like a very small regularization on the correct norm which we want, then the global loss needs will converge towards the global minimizers will converge towards the max margin solution. So basically this is how we connect it to like the training time, but the main proof is going to be that every max margin solution has these features. So typically max margin analysis is used to sort of understand generalization in new neural nets, like why do they perform well on test given that they haven't just given that they have used like finite training samples. But in this talk we are going to use it to characterize learned features. Yeah, okay, are there any questions till now? Okay.
Maybe, Depen, do you
Yeah.
have like a specific example of what a Fourier feature exactly looks like and how it's implemented by a given neuron or something like that?
Oh yeah, so when I say Fourier features, I guess I can, okay, I will definitely come to it afterwards, but we can basically think of it as, if we look at the let's say we look at this wait, where was the network? Yeah. If we look at the embedding weights, let's say we just consider U, what we will see in finally trained network is that this U will have a so this U for a given neuron is a vector of size P. So what we'll see is basically this will be like this will have a single frequency of either sine or cosine on those p dim. So if we do a discrete Fourier transform of a single neuron of U, we'll find like it has support on a single frequency. Does that make sense?
Yeah, that makes sense.
Okay.
Thanks.
Yeah. Okay. So given this, okay. So let's first consider the setup. So we'll consider a two-layer neural net denoted by f of theta, comma x, where theta represent the parameters and x is the input. For now, we'll assume a binary classification task because the proof technique is easiest for binary classification, but we'll extend it to multi-class as well towards the end, because modular addition is really a multi-class classification task. So in this case, we know this is how for a binary task, this is how the margin is defined. Like for the true class Y, we just take the neural network's output on the true class and subtract the other class. Now we'll do some manipulations. Okay, first let's define what margin means. So this is what the maximum margin means, that given parameters lying in certain space, which will be a normed space. So we want like, okay, for parameters whose certain norm is less than one, we want to find the parameters which maximize the minimum value of this margin across the entire data set. So this is what max margin means. So we can manipulate it a bit, and we can say, okay, we can consider any distribution over the training points, and then the definition remains the same. Now, this is the crux. So now in this case, for the second to third equality to hold, we really need to use the fact that the output f is a linear function of the neurons, as well as this margin is also a linear function of the output. That's why the second to third equivalence hold. That's why we can say like, okay, what we are going to consider is a distribution over neurons of the net. And then this thing is precisely the same as this thing. I guess I'm not exactly showing the proof, but the proof basically lies in the fact that f is a linear function of the neurons and margin is a linear function of f. And that's why these two things are the same. So this is what margin means. This is how, so till this point, we have simplified max margin, where it is now a function of distribution over neurons and a distribution over the data set. So this is going to look like a game. So we are going to play a game where we really want like to find like a balance between like what neuron to use given what data point to use. This is like a game theoretic perspective on what the max margin problem looks like. So at this point, okay, although we have simplified it till this point, like this doesn't really tell us how do we solve it. So the main technique behind solving this is going to be to find a pair D star comma Q star such that D star is the optimal neuron distribution to use for the given distribution Q star, and Q star is going to be the optimal distribution for the given distribution D star. So there is like a simple proof. I'm going to cover that in the next slide, but which basically shows if we can find a pair like this, then these are basically the minimax or the maximum solutions. So this pair is going to be like the main sort of proving tool for finding like explicit max margin uh, solutions. Let me quickly just show the proof of this thing as well. It's not hard. Like basically from minimax theorem, we know that max min is always going to be less than min max. But then because we have this pair of D star comma Q star, we can make like a bunch of substitutions. I guess we can replace the pair by like the distribution Q star so that min max. Okay, maybe there's like okay, all of these substitutions are basically like some manipulations which we can do, and this will basically lead to the fact that given this pair, we can show that the min max is also less than the max min, and thus both of these are basically the same. So all of these are same, and thus D star comma Q star is like the optimal solution for this particular max min problem. I guess I went too fast over this, but let me know if this is like not clear at all. I can try to explain it once more.
Just a quick question. So
Yeah,
you don't have a priori, you don't have some convexity concavity that lets you commute these
yeah,
curves.
yeah,
So essentially, you only know that they're equal if you find this pair,
yeah.
but you don't know a priori. Okay.
No, we don't know this, but we are going to show that such a pair is there, and thus these two are same.
Okay. Thank you.
Yeah. Okay. So this is basically okay. So this is basically going to be the max margin game which we are going to play. So we are going to find like this distribution D star and Q star such that both of these are optimal for each other, and then we are going to say, okay, we have solved this game now. So this is basically how the steps look like. So since our data set is so modular addition is a symmetric data set, so we are going to guess that Bob plays basically the uniform distribution over all the points. Then we are going to just solve this for a given neuron. So the main point is we can think of this as a distribution over neurons. That's why we can find like what are the best response neurons which we can use. Then we're going to construct a distribution D out of these things such that uniform is really like the best uh, response for Bob. So basically, this is how the entire technique looks like, and we are going to use. So the main thing which we are using is that these data sets are very symmetric. So we know that uniform should be kind of optimal for the maximum game, and then it's basically just like plugging the uniform distribution and finding the best neurons, and then some clever construction of the net for which we basically find all the data points are on equal margin. That's the basic game. But So in this entire thing, I skipped one thing. So I used binary classification while we actually want to do a multi-class classification. So why did I do this? Because multi-class classification margin is not linear and anymore. So this basically breaks down the whole proof. So basically, we can't use this technique which I did of changing this to an expectation over neurons and all these things, because margin is not linear anymore. So for getting around this task, we are going to do something called as margin prime, which we call as linearized margin. So we are just going to put some weights on all the classes which are not the true class, such that the sum of the weights is one and the weights are positive, and where we are going to just solve exactly what we did, but for this particular linearized margin. Now the whole proof works. Like basically we have a linear margin, all of these things. So the entire technique goes through. But then the question is, are we really doing like, is what we find using this, is this really the solution for this? The main point to note in this case is that this is an upper bound on this thing, because we are placing mass on things which are not even the maximum. So margin prime is basically an upper bound on margin. So let's consider this thing. So we have a G prime, which is an upper bound on G. If we can prove that the place where G prime is maximized, G and G prime are the same. So this is also the maximum of G. So this is what we are going to do. So we are going to find the maxima of G prime. Then we are going to show at this maxima, G prime and G are also the same. So this has to be the maxima of G. I hope this makes sense. If this doesn't, then please let me know. Okay, so in this case, I'll move forward. And so this is basically how the game changes now. So for multi-class classification, we also need to guess the weights tau on the classes. And then we also need to show towards the end that whatever network we have, margin prime is the same as margin for that, which basically means like, in some sense, this condition basically means like whichever classes we have put any weight on, those classes have to be on the margin for the given network. So this is basically the entire technique which we use. And for modular addition, it turns out that you can also put like equal weights on all the other classes. So you literally start with a uniform distribution and equal weights on all the other classes, which solve this, get like whatever neurons we have, and then construct a net and show that this net has margin prime is the same as margin. So this is the entire technique. And I'm not going to go through like actual calculations of this thing and what happens, but let me just try to sort of show like so the specific thing we are going to use in this work is that we are going to use quadratic activation. This makes the analysis much easier. I think analysis can be repeated for ReLU as well, but we have not we have not done that till now. But I think it can be done. So now in this case, let me just show like when we actually train a neural net on these things, how do the embedding weights look like? So this is just maybe one of these. This is just U. So we'll just show as we train networks, how do the embedding weights look like? So as training progresses, we can see like these really become like really become like one sparse in the frequency basis. So this is what we have basically shown in the work is that if we place uniform distribution on the data set and on the classes, we can really show that one sparse frequency neurons are the only ones which maximize the margin in that case. And then we have given a construction using these one sparse neurons such that you have all data points and all classes on the margin. Okay, let me know if this was not clear. Maybe I can show just final result and then I'll stop for questions on this part of the talk. So this is basically what we have shown in the work, that basically if a quadratic net has a width, we require some width to construct the net. So our proof only holds if the width is greater than 4 times p or something like odd order p. Then we can provably show that all neurons are of this form, like they have a support on a single frequency, and we can explicitly characterize like the precise max margin value. And this is like a practical run. So we trained a net with some small regularization on the norm which we use, and we basically see that it reaches precisely the thing which we have said, like this is the max margin, and it basically reaches that after some amount of training. Okay, so this is like the complete result for modular addition case, and I'll stop at this point and let me know if you have any questions on this part. Okay. In that case, I'll move forward. So let's cover the results for the group composition task as well. So group composition task is basically let's say we consider some group G, and we consider two elements A, comma B belonging to the group. We can consider permutation group as well. And what we really want the neural network to learn is to learn composing A and B. So in case of permutation group, we want it to learn composing, how to compose two permutations, and the answer is in the basically the result is a third permutation, which we want the neural net to learn. Again, in this case as well, we are going to analyze quadratic activations. So the inputs are going to be one hot vectors, and the out. So basically, if it's a permutation group of order k, then the input length is going to be k factorial for both A and B, since they're like k factorial elements in the group. So this is how the inputs look like, and we basically have the one hot outputs as well. So the number of classes are also k factorial. So this is how the entire architecture will basically be a sum of these single neurons. And I'm not going to go into the proof of this as well. Like I'm just going to tell what is the final result. So okay, so only for the groups S1 to S5, what we basically show is that for a network with width at least this, where this is like dimension of irreducible representation R, we can discuss this more for sure, but for now I'll just provide like the basic result. So what we basically show is that every neuron, like it was spanned by a single frequency in the previous case, will show that every neuron is basically spanned by a single irreducible representation of that particular group. And we can explicitly derive like the max margin in this case as well. And we basically see that the max, like basically it slowly tends towards the max margin as training progresses. Like this is a harder task, so we believe like actually exactly reaching the max margin might also be hard, but yeah. So this is the result for symmetric group. I'll also stop now to if people have any questions on this thing. Yeah. Okay. So in that case, I'll move forward and basically provides like the main future work directions out of this. So basically in this work, we explained like, so previous works had seen these emergence of Fourier features and irreducible representations when neural nets are trained on these tasks. So in this, we basically provide an explanation for those by using the max margin perspective. At least I really think like some of these, we can extend these things to transformers and like try to study like other intriguing phenomena such as length generalization. We can really try to see why certain positional embeddings work, why certain fail, and this can really help us in deciding like what principled positional embeddings we can use for a given task. So that we get some nice properties in transformers. I guess there has been a recent work on something called generalization on the unseen, which is basically when we split the training data set into something so basically, if we split the training data set into two parts where we explicitly leave out certain information of certain coordinates or certain subspace, then some people have shown like what neural networks tend to fill in that space with. I think this work can be used to sort of extend that line of work to other interesting go-to scenarios as well, and this will help us in understanding how neural networks behave on some out of distribution settings. I think that's all. Thanks for in inviting me for the talk, and I guess I hope like please ask questions if you have any. Yeah, thanks.
Thanks so much, Depen. This is a really nice talk. So let me stop the recording now.